We now come to some miscellaneous items of equipment without which electrical engineering could not function. The first one we look at is the relay. Briefly, a relay is a device for switching on a circuit from a distance, using a low voltage circuit to do it, or of course, switching it off again. It's very simple to understand. The main item in a relay is a coil with a soft iron core mounted on a base. Pivoted near the coil is a small bar without a contact at one end and a spring at the other holding it away from the coil. A second contact is mounted on the base and connected through it to a terminal. Another terminal is connected to the pivoted bar. It works like this. When the distance switch is closed, the current flows in a coil, making it an electromagnet. This attracts the pivoted bar, and the contacts come together, completing the main circuit. When the distance switch is opened, the spring pulls the contacts apart, breaking the circuit. Some relays work the other way round, like this one. The contacts are normally held shut by a spring, and when the current flows in the coil, the contacts are pulled open. Leaving relays now, we come to the principle behind nearly all the meters we use for taking measurements on electrical circuits. A coil of wire is suspended between the poles of a permanent magnet. The coil is connected to the terminals of the instrument through a spindle and balance springs. A pointer is fixed to the spindle and passes over a scale. In use, a known proportion of the current in the circuit is led through the spring to the coil. The coil, like the armature of a motor, rotates against the springs until the rotational force is balanced by them. The amount by which the coil has turned is shown by the pointer on the scale, and this is a measure of the full current in the circuit. This simple principle can be adapted to measure any of the quantities we might need: amps, volts, ohms, and so on. Next on our list of electrical equipment comes the potentiometer, which is used simply to vary the voltage across a load. It consists basically of a resistor with terminals A and B at its ends, and a sliding contact connected with a third terminal, C. The sliding contact can move from end to end of the resistor. In use, the potentiometer is connected like this. Terminals A and B are connected across the voltage source, and terminal C is connected to one side, in this case the negative side, through the load resistance, a lamp, say. So the load and resistor form a parallel pair. If the slider is at the right-hand end of the resistor, there is no voltage across the load. If it's at the left hand, the full source voltage is across the load. The voltage across the load will vary uniformly from full voltage at A to 0 at B, at intermediate points of the slider. Notice that because the load is in parallel with the resistor, the effective resistance of the circuit is reduced. Therefore, by Ohm's law, the total current is increased. If sensible control of voltage is going to be achieved without violent current fluctuations, it can be shown that the load resistance should be much greater than the potentiometer resistance. In practice, a potentiometer often looks like this. The resistor can be a coil of wire bent round into a circle with a slider rotating around it, or it can be a carbon track. Of the three terminals, the center one connects with the slide. There's another use for a potentiometer. It can be used as a dropping resistor. For example, if you have a supply of 20 volts and a lamp, say, designed to operate at 6 volts, you have to lose some volts somewhere in the circuit. You could do this by putting a resistor of just the right size in series with the lamp, so that it uses up 14 of the 20 volts. Or you could do it by using a potentiometer with the slider set to give just the right resistance to drop the voltage by the right amount. Used like this, with only two terminals connected, the potentiometer is called a rheostat, a device which actually controls current flow in a circuit. If the sliding contact is at the A end of the resistor, none of the resistance is in circuit, and the current will be a maximum and the lamp will be damaged. If the contact is at the B end of the resistor, all the resistance is in circuit, and the current will be a minimum and the lamp will not light. In this case, if the current control is to be effective, it can be shown that resistance of the rheostat and the resistance of the load should at least be of similar size. And there we'll end this short review of some pieces of electrical equipment. In the next part, we'll be talking about earth grounds and short circuits.